The delta function is a special and foundational function in signal processing. Here, I'm going to quickly define it in continuous and discrete time with a few examples. In continuous time, the definition comes in two parts. First, we say delta of x is equal to infinity if x is equal to 0, and 0 else. Then we say the integral from negative infinity to infinity of delta of x with respect to x is equal to 1. The delta function is not strictly a function, but it doesn't seem to really matter in application as long as you observe the definition. Let's set the function up in a system, then plot it. Our input variable is t, which is drawn from the real number line. Our function is delta, and our output variable is y. If we plot it, we make a line that is 0 everywhere except when the argument is 0, which in this case is when t is equal 0. Because the value at t equals 0 of the function is infinity, we represent it by an arrow, like we do the axes of our plot. We call this an impulse. To denote the hypothetical area of the function as 1, we write a number 1 next to the arrowhead. Next, let's do an example of a modified delta function. Plot the following function, 5 times delta of t minus 3. The argument of the function is 0 when t equals 3, so we draw an impulse at t equals 3. The area of the delta function is by definition 1, which when multiplied by the constant 5 is 5. So we write a 5 next to our arrowhead. Finally, consider what happens if the delta function is multiplied by another function, for instance, 2 times cosine of x. First, we plot the two functions being multiplied on the same axis. Second, we note that if these two functions are multiplied, then the value is 0 everywhere except when the delta function has a non-zero value, which in this case is at t equals 0. The height of the resulting function is still infinity, but the area is now 2. We conclude that the delta function, multiplied by any other function, results in a scaled delta function. Said another way, if you multiply a delta function by another function, you are taking a sample of that second function, wherever the delta function is non-zero. Next, we consider the delta function in the discrete case, which is considerably more straightforward. In the discrete case, delta of n is equal to 1 if n is equal to 0, and 0 else. Again, we set up the system in plot. Let n be drawn from the real integer number line with system output k. The plot is simply a lollipop at n equals 0 with height 1, and 0 for all other n. The properties of shifting and amplitude, scaling, and sampling discussed in the continuous case apply to the discrete as well. Let's work an example. Plot the function 3 times delta of n plus 2 times cosine of pi times n, and provide an equivalent simplified function. Step 1. Break up the complicated function into two easier ones, 3 times delta of n plus 2 and cosine of pi times n. Step 2. Plot the two subfunctions on the same axis. Step 3. Multiply the two functions point by point to plot the resultant original given function. And step 4. We recognize the original function as 3 times delta of n plus 2.